All right, this is the immunity lecture. The word root means immune. To be free of a burden. So the immune system protects us from illnesses. Works by a learning process. So that learning process is a two-step process. So the first thing you got to do is recognition. The recognition process is, like I mentioned earlier for the lymphatics lecture, the white blood cells have to be able to recognize self versus non-self. Can't do that, you're non-functional. Okay, but once you can recognize something that's non-self, then, secondly, there has to be some, you have to follow up. You have to have some mechanism of destruction. Okay, so recognize and then destroy. And then, so what I have on here are a couple of things, what we call the lines of defense for the human body, but also categorized as specific or non-specific. So, a non-specific defense is the recognition of anything that's non-self. So any pathogen, anything non-self, they're all how should I say this? They're all part of the non-specific defenses. So just keep all the bad guys out, okay? However, versus specific defenses, basically your immune system is adapting to a particular bug. To one particular, I'll say pathogen. So those are the two categories, specific and non-specific. In non-specific, keep all the bad guys out. Okay, you know, just anything that's non-self is, you have defenses that can just keep all the pathogens out. But if, you know, one gets inside you and then there's one particular pathogen that you want to mount a defense against, those are your specific defenses. So just kind of keep that in mind too. So to go through the levels of defense, lines of defense, levels. Hold on a second. Somebody messed up the whiteboard. Huh? first line of defense. Membrane barriers. Well, that's easy to understand. Just keep them out of your body. Don't even let them in. Membranes do that quite well. For example, when I say skin, skin is a cutaneous membrane, and it's not even letting the pathogen inside your body. Mucous membranes are a good example. Like lining your gut, lining your throat, things like that. Keep things out. Oh, stomach acid, HCl. That's a good chemical barrier in the stomach. So things that you ingest, the stomach usually is a good destroyer of most things, and it's secreted by the stomach mucosa. But if things get inside your body, it gets in your bloodstream, it gets in your connective tissues because you got a cut and something got on you, you stepped on a dirty nail or something. Then you have your second line of defenses inside your body. I'll just put second. What you see there is basically your mobile unit of phagocytes that circulate in your blood. So phagocytes are cells that eat garbage. Macrophages are the primary one. They're derived from monocytes. Okay, you're already supposed to know that. So macrophage. Eosinophils, dendritic cells. I'll just kind of list the ones I have there. These are part of your non-specific defenses. They have the ability to recognize anything that's non-cell. In fact, the macrophage has this receptor called the scavenger receptor. Right? It's just scavenging for anything that's non-cell. Anything that suffices to produce recognition by the scavenger receptors, like garbage. You eat it, you get rid of it. Anything that's non-cell. All right. And then you have your third line of defense, your specific defenses. These are the lymphocytes. The B and T lymphs. Now, I'm going to spend a lot of time talking about those today. So, a couple of things right off the bat. This is the part where I said you kind of adapt to it. It does require exposure. I'll put in parentheses 2 antigens. Sometimes I abbreviate that AGs. Okay, and that'll allow the whole adapt to and mount a defense kind of thing. You recognize and you mount a defense, and I'll get into the details of that. So I just want to mention that now. So those are your 3 lines of defense, and what I didn't mention for the second line of defense are these cascades of molecules that help fight against bacteria, but I have slides on those, so this is just kind of an overview. But let's remember one thing, that the white blood cells I'm talking about today come from the bone marrow. It's kind of seek and destroy cells. And I already talked about how they're developed, and I already talked about the function, the basic function of some of the lymphocytes, so I'm just going to fly through these slides. Eosinophilia is a condition where you should see a higher than normal eosinophil count. And on this slide, I'll point to them. That one, that one, that one, that one. There's one up there that exploded. All right, let me get to. All right, this is where I haven't taught yet. I want to lecture first on the non-specific defenses. Your book sometimes calls them innate. I don't use that term. Non-specific. I like that better. So we're going to talk about interferons and complement. So the nonspecific defenses do not distinguish one type of threat from another. All threats are bad. Their response is the same regardless of the invading agent. So I already mentioned the phagocytic army of cells. Generally speaking, they utilize what's called the inflammatory response, where you vasodilate the area to increase blood flow, and that will attract leukocytes via chemotaxis. So here's the example of the inflammatory response and chemotaxis you can learn from. Inflammation. If you get a cut, how do you know it's infected? The white pus, because the white pus are the white blood cells that have been attracted to the area to fight the infection. All right, well, they have these nice steps I'll follow. Step 1 says leukocytosis. Leukocytosis is, you just have to be in the bloodstream. You form in the bone marrow, but if you never make it into the bloodstream, you can't help. So, enter the blood, enter circulation. The WBC enters circulation. In this case, it's the neutrophil. And then if you look at the dirty nail, there's a couple of things. There's the green capsules, and then there's those little blue molecules. The green capsules is the infection. That's the bacterium you want to destroy. The blue, this blue thing right here, the injured cells will release a chemoattracted protein. Okay. And so, but that's kind of like, what it's going to do is, it's not really mentioned, but chemoattracted proteins, just like the name implies, it's going to attract something, the white blood cells. They provide a chemotaxis trail, you know, a little gradient for the white blood cells to sniff out for WBCs to follow, a little trail to follow. Okay, so that's why they're there. What's not mentioned is at the area of infection, the blood cells are going to stick. So the endothelial cells of this blood vessel will start to make these adhesion molecules. Endothelial cells produce adhesion molecules. Okay, so I'm filling in the gaps that they don't talk about. Because then you get to step 2, they say margination. I'll say adhesion instead. Because your white blood cells are in constant circulation. And you only want them to stick to where there's an infection. So that's why you only have production of the adhesion molecules when you stepped on the rusty nail or something. So, you know, what happens is, you see how like you're flowing and then they go like this? They're trying to show you that it's rolling. And then it stops. Okay? So it rolls to a stop. It rolls, slows, stops. It's adhered to the vessel wall. Okay, then you have step 3, diapedesis. Sounds like a fancy word, it's not. What's PED refer to usually? Pedal. PED, what's it refer to? But di means dissect, it means jump across. So that's what they're showing you there. You roll, you stick, and you get sucked through the membrane of the vessel wall. WBC. They use the word squeeze, I like that. Squeezes through vessel wall. I mean, you have to enter the connective tissues to fight the infection. Okay. Now, the reason why they're doing that is they're attracted to the chemo-attractant proteins. Okay. It's kind of like they can sniff it through the vessel wall, and they just kind of like squeeze through and follow the trail. And then so step 4 they call chemotaxis. And how they word it is good. I'll just write what they say. Follow the chemical trail. You could do this in the lab. You could put a well and just fill it with chemoattractant proteins and put a porous paper membrane on top of it and put cells on top of that, and the cells will just get sucked right through to the bottom. They really do have an ability to squeeze through things once they get a sniff of the chemoattractants. So here's a picture of the destructive forces of inflammation once you attract the white blood cells. And well, they show the little green bacteria being scavenged by the macrophage. Okay. So another defense against viral replication are these molecules called interferons. So take a look at that as I recondition the board. All right, you've looked at it. Which cell gets infected? 1 or 2? 1 gets infected. Okay, so let's kind of outline this. Host cell 1 gets infected. How viruses work is they hijack cells, and what they do is they take their genetic material, RNA, and they infuse it into the host cell, therefore taking it over. And that's how they replicate themselves, by using the host cell's genetic material. So their genetic material happens to be RNA, and RNA can be reversed to DNA, and so what they do is, as a defense mechanism, after they get in, the host cell 1 puts out like this red flag warning. It makes these proteins called interferons. Host cell 1. virus infects host cell 1. It does that by hijacking the viral RNA is converted to DNA, and that viral DNA inserts itself into the host genome. So viral DNA inserts into host cell 1 DNA. There's a reverse transcriptase that allows RNA to go back to DNA. I had to mention that. Someone won the Nobel Prize for that work, that RNA can go back to DNA. It used to be DNA, RNA, protein, that's all they knew. And then when this came out in the 70s, so I at least had to give mention to that. So basically, you've hijacked the cell, you've inserted your genetic material in it. But in response, host cell 1 secretes the interferons. And look what happens. Host cell 2 responds to the interferons from host cell 1. The interferon synthesizes protective antiviral proteins. Host cell 2 reacts to interferons. I'll put in parentheses, from host cell 1, just keep track of the two cells, right? Makes antiviral proteins. And as the picture says, they're supposed to block the viral replication, the viral reproduction. So notice that in this mechanism, the interferons work. They protect host cell 2, but they do nothing for host cell 1 because that cell's already been infected. But that's how you mount a defense. Host cell 1 took the hit, but if you can block the replication, you can get better. I guess the question becomes, what if you can't? You might die. I mean, right? I mean, viruses do kill people. Influenza kills people. I mean, viruses can be lethal. But if your body can have some, what's called correlate of immunity, just something that your body can produce to mount a defense that can actually block or kill, then you'll live. And that's interference. Here's another example of a good defense mechanism. It's called complement. It's a cascade. It's kind of like when we did the blood coagulation. You had the cascade, you had those complexes that form, and it's kind of like that. All these molecules that come into play. Now, these molecules, I kind of like it when they kind of name the thing for what it does to help us remember. Like, for example, these are called interferons because they interfere with reproduction. So I kind of like that. This is kind of the same way. Complement is a series of molecules that complements both the specific and non-specific defenses. Okay, on the top there, you see all these pathways that can trigger complement to work. Let's just do one of them. Let's do the classical pathway, where that says activated by antibodies coating target cell. Now antibodies, I'll talk about them later. We've been talking about them in terms of blood typing, but they're immunoglobulins. They're proteins that circulate, and they're your simplest ammunition for defense. Okay. What I like to say about them, they're not the murderers. They're accessories to murder. I guess it's garbage day. Activated when antibodies coat target cell. Sometimes I just go ABs for antibodies. So let's say you have Mr. Pathogen. I'm going to get rid of it. And you know, pathogens, they have all these surface antigens that you can recognize. And your antibodies, your simplest ammunition for defense, they kind of bind them. And they kind of coat. That's what I'm writing. They coat the antibody in. Well, something that happens is these antibodies, as they circulate, they call the forked end the specific end. They may be specific for those little red antigens on the pathogen you're trying to get rid of. But the tail end is considered like non-specific. The non-specific end, it may randomly, or not so randomly, bump into a component of complement, like for example, C3b, there. Okay, and the non-specific end may kind of like bump into that complement. And what it'll do is it'll like fix it to the pathogen. Right, kind of comes along for the ride. They call that complement fixation. So by doing this, they call this opsonization, where you coat pathogens with the antibodies and you fix complement. What you're doing is you're increasing the chance that this thing will be phagocytized. By coating pathogen with ABs and fixing complement, you increase chances of phagocytosis. Because remember, that's the destructive mechanism, phagocytosis, not the coating. Antibodies are accessories to murder. they're not the murderers. That is, okay? And complement fixation helps increase that chances. So that's why this is called complement. You're complementing the coding of the antibodies, increasing the chance for phagocytosis. That's how you complement the specific defenses. Let me write that as the title over this. Complement, quote unquote, right? It's what they call the thing. Specific defenses. You also complement the non-specific defenses by enhancing inflammation. Quote unquote, complement non-specific defenses by enhancing inflammation. So just very simply, I'll just state what they state. You stimulate histamine release. Okay. Those are basophils. Increase histamine release. That's all I'll say for that. So, to summarize, I'm not done yet, but so far we got number 1, complement specific defenses by this whole complement fixation thing. Number 2, complement non-specific defenses. Number 3, MAC attack. If you can do complement fixation or something like it, you can trigger this cascade of things. I won't make you memorize all of these molecules. Just know MAC attack, because what you're doing is you're forming this membrane attack complex to punch a hole in the cell membrane of the pathogen. MAC attack. What's the M? Membrane attack complex. I'm not going to write it out, just know it. And look at that, you punch a hole, that causes lysis. Punch a hole. I think that's clear enough. Causing lysis. Because water will rush in, lysis is just bursting. So that's the mechanism of destruction. The third thing, okay? And well, that's complement. That's how complement is a non-specific defense for us. But I'm going to change gears here now. We're going to now switch to the specific or adaptive defenses. And so the lymphocytes are the B and T lymph. We'll talk about those primarily in their subpopulations. And the experiments that helped us know it's the lymphocytes that have the immune function were done in irradiated mice. If you zap a mouse with high energy waves, you kill cell function. So they're doing this to try to get a mouse model for experiments. And so in a normal animal, if you inject them with some antigen, you'll mount to a normal immune response. Right? Remember, it's the antigens, you require exposure to the antigens. However, if you have an irradiated animal where you kill the cell function, you inject with antigen, no immune response. So there's your model. Because now you can conduct experiments to figure out which cells are responsible for the immune function. So if you inject, say, irradiated, cell function gone, which cells, give them the antigen, give them some random cell, maybe connective tissue cells, some other cells, and you get no response, how do you interpret that result? These cells don't have the immune function, right? If you inject the irradiated animal with the lymphocytes and give them the dose of antigen, and the immune response is restored, what do you conclude? The lymphocytes have the immune function. So R is exposure. So these are specific defenses. Respond to a particular bacterium, but you're ineffective against any other foreign invader. Okay. kind of like the non-specific defenses are like a cop on patrol. What kind of trouble are you looking for? Any kind of trouble, all right? All the bad guys, I guess you're looking for. But if you're a detective and you're assigned a case, you're assigned to look for, you know, one bad guy who committed one particular crime. So it's like these defenses are like that. You're sensitized against one thing that you're going to fight. That's why you get the flu shot every year. They're trying to anticipate what's going to be circulated this flu season, and they put that in the shot you get. And you mount all of these defenses to build up your antibodies, so if you actually get it, you're protected, you're immune from it. So the exposure could be, like I said, if you get a vaccination, that's deliberate. You do that on purpose, so you get the memory cells, you get the antibodies, or you can do it accidentally, right? From a sick classmate, sick family member comes over, get you sick. Okay, so lymphocyte, it's lymphocyte dependent. The B cells, sometimes I call them B lymphs, B cells, same thing. The ones that are B. There are subpopulations. Okay, so let's say you're a cell circulating. Remember what the lymphocytes look like? They have these huge, dark nucleus, little in the cytoplasm. And their receptors are these membrane-bound antibodies. Okay? Membrane-bound. Those are their receptors. And let's say that particular antibody is specific for this little red ball antigen bug, AG antigen, right? And you bind it. You're like, oh, okay, that triggers a response. And what happens is, well, this cell can't do anything. It doesn't even have any cytoplasm, so it has to kind of like develop. And the first thing it does, it may just proliferate. It'll just multiply, cell division. So I'm going to draw a couple of them. This clonal expansion, as they call it. This one blue cell is a particular clone of all of your B cells. Let's say you got a green one. But their membrane-bound AB is not specific for this particular antigen, so they're not in the game. They're not going to clonally expand. But the blue one is the clonal expansion, the one you want. And maybe this one will then further divide into other cells. Draw this one this way. I'm drawing ER and Golgi. I'm making a bigger cell with more cytoplasm. This one is your antibody factory, right? You need some cells to make the antibodies. And not only are they going to well, they're going to basically secrete them into circulation. So these are the immunoglobulins that circulate in your bloodstream. This is called the plasma cell. This cell is not a plasma cell, it's not your antibody factory, but it's gonna it has a memory. It's like, I'm gonna remember this. So if this ever comes back again, I'm gonna mount a faster, stronger response. We call those the memory cells. You got them forever. They last decades. And those are your subpopulations for the B lymphs. Now the T lymphs have different subpopulations. I have TH, that's helper T cells. Sometimes they're called CD4 cells. This membrane protein that helps them trigger responses. But no both, helper T, CD4 is the same thing. And okay, let's see. Well, I'm going to tell you their function. They're kind of the linchpin of the whole thing. Well, let me put it this way. If you eradicate the CD4 cells, basically that's AIDS. They're really important. We have TC. Those are the cytotoxic T cells. These are sometimes called the killer cells. They can do the hand-to-hand combat. They can literally attack virus-infected cells one-on-one. So I'm going to call them killer cells. Sometimes they're referred to as that. I'll have a slide on that towards the end. I'm not going to talk about the T regulatory cells so much. Before I move on to those, these are also called CD8 cells. So the cytotoxic T cells, CD8, the T helper cells, CD4, also known as that. Okay, then T reg stands for regulatory. These are like suppressor cells, also known as CD25. They're like a brake on the system, so you don't have an overreaction. A brake. Like a car brake, stop. So that way, well, put it this way, people who have a problem with this subpopulation of T cells, they have autoimmune problems, they have severe allergies, because you can't stop it once it starts. But that's all I'll say about these. Then of course you have memory cells, and the memory T lymphs that help a lot are the CD4 cells. So I'll put that. Memory T helper cells. So that's kind of an overview of all the subpopulation of the B and T cells. I want to first talk about B cell mediated immunity. So these two major groups, think of the B cells as one arm of these adaptive defenses, the antibody cells. And think of the T cells, these killer cells, these T helper cells, as kind of like the other arm of adaptive immunity. The B cell mediated immunity, well, but they both require antigen exposure. And so the red, this represents the bacterium presenting different antigens. So these shapes represent the antigenic determinants. And like I've been saying, specific defenses, what makes it specific? It's the ability of antibodies to recognize these specific antigens, because they are what are going to provoke the immune response. If you're a larger bacterium and you present more antigens, you increase the chance that you have antibodies, an antibody subpopulation that they're going to find it. And so I think the greatest advantage we have is the diversity of these cells. I already defined plasma and memory cells, but the antibodies, again, I said earlier, they're the simplest ammunition of the immune response because they have such great diversity. Now, there's something I'm not going to go into detail. Is the reason is for the diversity is this something called somatic recombination, this shuffling of that part of the genome in your DNA. And you can look that up if you want to know more about it. You might learn about it in a molecular class. Well, let's just say that the result of that, of the reshuffling, is you get 10 to the 11th power different specificity. That's a big number, right? Yeah. And you can appreciate that many different kinds of clones put out by your bone marrow, right? So if you get sick, you'll likely get over it in a week or two. Got to give the antibody time to build up. So I won't get into too much detail here. The fork region is the specific region. The stem region is non-specific. the primary and secondary responses is more of what I want you to know. We kind of outlined it already, where when you have your different clones, they illustrate 3. This one in the middle is specific for this antigen. So that's the clone that proliferates or expands, and then they further expand into plasma cells or memory cells. The plasma cells are going to get you well now. It may take a few days, a couple weeks, but you kind of wait for the antibody titer to get up to fight the infection. And of course, these will hang around for next time. So these are, it's not the first rodeo, right? They're the memory cells. They're not this one, it's this one. So if you get sick by the same bug a second time, well, you mount a faster, stronger response. And you may not even get sick. Okay? So that's kind of shown here. The antibody titer to antibodies A, it's kind of like this high, then weeks later you get it again. It goes up faster and stronger, you don't even get sick. But a different bug, bug B, antibodies against B, it'll be the same response just like before. So the primary, secondary immune response is different. So what the antibodies are doing, this first row here, this isn't the killing mechanism, but this increases the chance that your body will get rid of it. So, remember I said earlier, fixed complement, punch a hole, that leads to the cell lysis. That's the destruction. All of these here precipitate, agglutinate, neutralize by coating. All of these don't eradicate, but they enhance the chance for inflammation, histamine release, and phagocytosis. And this is the destructive mechanism that follows. All right. Now there's different kinds of immunity that we define. And it's good to get it. So we call it acquired immunity. And this is a good thing. So let me define these terms. To build up a strong immune system, there's active immunity, there's passive immunity. Acquired immunity. There's active, there's passive. Simply put, active is you're going to get a T cell. We're being invaded. Hey, Jeff, you need something, Justin?
Mini-me, muscular man.
Oh, yeah, that's right. Oh, it's right there. It's behind the hood.
Thanks.
No problem. Good. So you get the memory cell. Passive is you just receive the antibodies. So I'll just say, just receive ABs. Okay. Which one do you think is better? If you had to guess. Well, I would say active is. Those memory cells last like forever. These are just proteins. They may circulate for a little while, and then they're gone. Okay. Usually, you don't do this one unless you're close to death. Like you don't have time to wait for an immune response to get this. So this is kind of like, well, let's do it if there's some kind of last resort. So the active immunity, your immune system responds to it. Whatever doesn't kill you makes you stronger, but eventually you have memory cells for next time. Passively, just receive the antibodies, the immunoglobulins. Okay. For example, from breast milk, from nursing mother to baby, there's different subclasses of antibodies. The Igs, the immunoglobulin Ig. There's IgG. Yeah, this is the most common one. IgGs, those are the ones that can cross the placenta. The IgGs can cross the placenta, so that helps baby. They can last 8 to 10 weeks after birth to confer some passive form of protection for the baby. It's important for that fragile state of life. So on this slide, passive, naturally acquired, cross the placenta. In this example they give here, a nursing mother. So let's say, okay, these only last 8 to 10 weeks. Are you nursing? It's a choice. But if you are, it's usually 1 to 2 years. And in the breast milk, there's the IgAs in the breast milk. So that can confer another couple of years of passive immunity for baby. Okay. So these are examples of passive immunity naturally acquired. So let's do the other category of passive immunity, artificially acquired. Go to the clinic and just drop a bag of wide spectrum antibodies. We don't know, for whatever reason. Maybe you're not doing well. Good example is the snake bit patient. So passive immunity, artificially acquired. What you could do in preparation for this is give a small animal the snake venom, just a little bit of venom. And so then the animal will produce antibodies against it. So what you do is you harvest that animal sera, you call it the anti-snake sera. Harvest anti-snake sera. Obviously I'm leaving out a lot of details, but you get the idea, right? You made the animal who had a successful immune response against the little bit of venom, and you're going to use that for your clinic. You just give that to the snake bit patient. Okay, let's do the naturally, artificially acquired immunities for the active form. So you have naturally acquired under the active. Let me erase this. Kind of the right way. You just get sick. Someone gets you sick. You mount a response. Most of us get really annoyed when someone sick is next to you. right? If you're sick and you cough on someone, don't apologize. Just say you'll thank me later. You're getting a memory cell out of this, right? But that never works, right? We all hate getting sick when people are sick around us. That's just, the world we live in. We don't live in plastic bubbles. Something's going around. You might get it, you might not. Okay, artificially acquired, that's vaccination. The flu shot, maybe an elderly, they'll give you one against whooping cough. Newborns have a pretty regimented vaccination schedule, 2 days, 2 weeks, 2 months. I mean, they have it all worked out. But we're trying to protect against things that we know have been eradicated. But if you don't vaccinate, I mean, you could look it up. It comes in the news every once in a while. These things come back, right? So it's not that some people, we may be under this false impression. Oh yeah, measles and mumps. Oh yeah, we don't get that. It's gone. People haven't had it in years. There hasn't been a case in years. And you don't vaccinate, and people start getting it. It's like, what the heck? What's going on? Those bugs are still there. They never went away. We just haven't been getting sick because we vaccinate. But if you don't vaccinate, and all of a sudden you have a case, what does that tell you? Those bugs are still there. Okay? We just never had a case because most people vaccinate. And if you don't, you make whoever doesn't get vaccinated vulnerable. You're at risk. So that's something to consider. If you're a parent, for yourself, vaccinations work. That is well established. And people have different opinions on this. To me, it's not an opinion, it's an issue of public health. You have a conversation with me about it. It's a very short conversation. You have very strong feelings about it. So I vaccinate my kids in case you don't vaccinate yours. I want my kids to be protected. I think it's good, this is a good point to take a break. And so after our break, I will finish these slides. And then right after I finish these slides, we're going to go right into the written part of the exam. So there will be no break. I just want to give you that heads up. Okay. You'll have about at least 30, 40, maybe more minutes to complete that. It won't take you that long. Okay, so you have a break.